A larva is a distinct juvenile form that many animals go through before metamorphosing into their next life stage. It moves instinctively, searching for food while avoiding light. These simple and seemingly predictable behaviors are actually very useful to scientists, as they allow researchers to track changes in its routine when exposed to microdoses of various chemical substances. But what can we learn from these changes? And how can this tiny larval sacrifice be useful to us? In this quest, our Noise&Patterns team worked hand-in-hand with scientists from Wrocław Medical University. To track larval movement, the little volunteers needed to be filmed. Since they don't like light very much, high-sensitivity cameras seem to be the best choice. As for tracking, there are practically two ways to do this. One, by using the industry-standard algorithms included in Python libraries like OpenCV, or two, by using deep learning to teach the system what a larva looks like. We decided to test both methods, and here are our findings. Since the dark video recordings weren't perfect, OpenCV detection required calibration and the use of steps like converting to grayscale, masking to remove reflections from the petri dish, blurring, and thresholding to make our larva more distinct for computer vision. Also, eroding or dilating proved helpful, which, in plain language, means slimming down or thickening the image. Next, using the Canny algorithm, we detected edges, drew contours, and marked the center point as our tracking anchor. This method actually proved 100% reliable, but it limited us to one dish per detection. And as you can see, the calibration process can be too much if you work with a lot of samples. Deep learning, on the other hand, required more initial work and proved a bit less reliable, but once set, the detection workflow seemed much more pleasant. Several larvae could be detected at the same time and assigned to their respective dishes. So, we would likely lean toward this solution for potential future automation. Now, the patterns started to emerge and tell their story. The control group, meaning the larvae that weren't exposed to any substances, behaved predictably, going around the petri dish and sometimes taking shortcuts. The beauty of a rose diagram shows this behavior in the most elegant way. Just look at the larva's world map, compressed into a circle, sliced every 15 degrees, and the four main directions are instantly obvious: going north, going east, going south, going west, and sometimes taking shortcuts in other directions. The proportions are instantly visible, and pay attention to them as they will get more interesting soon. As is their nature, the larvae avoid the light source. However dim the light source was that we used, the graph called a heat map beautifully showed where they spent most of their time, and it is exactly as far away from the light as possible. They covered, on average, 20% of the space in 1 hour. This is another interesting indicator that could prove to be instrumental in future research. The most exciting moment, however, came when the scientists exposed the larvae to alcohol and energy drinks. As could be predicted, alcohol slowed the larvae and disoriented them. Interestingly, in some cases, it even changed their behavior, making some of them crawl toward the light, something unseen in normal, healthy larvae. The path pattern changed, something that, again, can be elegantly depicted and quantified in the rose diagram. In the energy drink group, however, the distribution of directional changes was not affected. The increase in speed was evident, but the overall coverage of the field remained more or less the same, allowing us to conclude that their behavior was not disrupted, just accelerated. This preliminary analysis opens many doors for further research, but also makes us consider a longer observation time window and, of course, how other substances, including bacterial solutions, will influence the larvae's movement patterns.